idea number 2. So we can't play very much with this. Let's play with this. And let's increase the rate of the formation of product, or K2, break down the enzyme substrate to make the product. But again, yet remember that you have a substrate, you have an enzyme that will migrate to each other, form the complex, do some chemistry, and then the product's going to leave. If we make the chemistry doing part very, very fast, we still are limited by the time it takes for the enzyme to migrate to the substrate, which means if we make this infinitely fast, we're still slowed down by A1. So it doesn't help us to go any faster than that. So these aren't very good ideas. So we need some new ideas. So one thing we can do is to provide a different mechanism for the reaction. And we know, for example, if you learn in organic chemistry, you take a reaction, you could raise the pH or lower the pH, and it goes faster. It's because you're involving the proton, either subtraction or addition to the process. So, and we also know that amino acid side chains have ionizable groups. So it makes sense then we could use these groups to help catalyze, act as an acid or act as a base to the substrate to make it react faster. And that's certainly possible. And the other thing we can do is form a temporary bond between the enzyme and the substrate and force it to react faster. So we have two possibilities, acid-base catalysis or covalent catalysis. These two work. Enzymes do this. However, we only get about a 1,000-fold increase in the overall rate of the reaction. And remember, we're trying to go for millions or billions or bazillions faster than without the enzyme. So this works, but not well enough. So let's try something else. Next is intermediate formation. What we're doing here is taking, this is our substrate, and so this is our product. What we're doing is taking a huge hill and breaking it up into little hills. And if we do this, then each step is going to be a little easier to do. And if we can do it in a series of small steps, then it should go faster. So if we do this, so this hill is not as high, or transition state energy is not as high as it would be if we had to do it all at once. But when we're going over here and taking it in short steps, then it should increase the rate of reaction. So let's go do some more definitions on this. An intermediate is a quasi-stable step between the substrate and product. It can be detected and occasionally isolated. Not guaranteed, but it happens in many cases. People are doing this. And think about this as baby steps. You're just taking little simple steps, one step at a time, rather than trying to do it on one giant leap. And again, we're going to get a gain of around 1,000, which is okay. But we need a lot more than that. We really need something big to drive the reaction faster. So now what we're going to do is look at this series of data. What I want you to do is notice that this, and this, which is our leaving group, is exactly the same molecule, isn't it? And then if you take a look at this, you'll see this bond right here, this bond right here, this bond right here, and this bond right here, which is being formed, is exactly the same in all of those cases, an acid and hydride bond. So if we're making the same bond, the same leaving group, and we're starting with very similar reactants, then the chemistry that we're doing is exactly the same. Chemistry is done. The only thing we're going to change is the R group, which is attached to the carbon, which has the double bond oxygen attached to it, the two acids. So let's take a look. So what we do is we measure the rate of the reaction when we have these two molecules coming together to form this. And whatever it is, we're just going to call it 1. We'll normalize it to that. Then what we're going to do is go to step number 2. And what's the difference between step number 1 and step number 2? Answer is, how many molecules do we have here? 2. How many molecules do we have here? 1. So this is a bi-molecular reaction, and this is a unimolecular reaction. Same molecules, same functional groups, same products, But look what happened. Factor 1,000 faster. But you notice we have some blue arrows right here, and that represents free rotation. So we can rotate this molecule in any particular conformation that we wish to do so. Now let's take a look at what happens when we go from step 2 to step 3. You notice that these groups are still tied together in the same molecule. We still have blue arrows, which means we have free rotation. But the difference is that this methylene group is now absent. So all we've done is brought it closer together. That's all we've done. We haven't changed its flexibility at all. But look what happened. Another factor of almost 1,000. Now what we're going to do is take this part, and you notice we still have these carbons. We have these 2 carbons right here. So this part is exactly the same as this. The only difference is we have some groups attached to it, and you notice there's no freedom of rotation. And what happens? It goes faster again. And if we look at the beginning to the end, we're talking about 50 million increase. Now we're getting to something that really makes things go faster. And this is what we want to do. So this works. So what are we doing in this process? Well, first of all, what we're doing is we're tying the 2 groups together into the same molecule. So we're pulling them closer together and keeping them there so they can't get away from each other. And the second thing we're doing is eliminating the freedom of rotation of the molecule so it can only be touching in a certain way. So this is what we're going to call the proximity effect. So this is where it looks like increasing concentration. Let's think about this for a minute. What does concentration really mean? Concentration can be looked at as the space a molecule can fly around in, like let's make a box. And inside that space is not going to hit another molecule of itself. The bigger the space, the more dilute the solution is. The smaller the space, the more concentrated it is. And also remember, we're talking about kinetics. It's the concentration which drives a number of collisions that can occur with any particular unit time. So by bringing the molecules together, we effectively increase their concentration. There's more collisions per second than it would be if we kept them far apart. So that's why we can think about this as increasing the local concentration. Well, what are we doing? We're limiting orientation by translation and rotation. And this decreases the effective energy entropy, because remember, entropy is the number of ways you can arrange an atom in space. And so if we limit where the molecules can be, we effectively decrease their entropy. So it looks like a decrease in entropy, and some people argue that that's kind of effect. But you realize in this particular example, we got a 50 million increase in gain. That is really, really good. But we're greedy. We want to find some more ways of making it go faster. So this will be the end of part